In this modern society of ours, it actually makes sense for us to conclude that statistics is actually one of the most applicable branch of mathematics, if not the most applicable branch of mathematics. My name is Abefe. I am a YouTuber, a content creator, and a full-time tutor, and welcome to my learning space. Let's get something straight. In this data-driven society of ours, having a basic knowledge of statistics is actually a very good skill. And for anyone trying to learn statistics from the basics, either from the basics or the intermediate level or the advanced level, we all ask the same question, and that is, what is statistics? So let's answer the question, what is statistics? So in my own way, statistics is actually that branch of mathematics that deals with how we collect, how we organize, how we analyze, and also how we present data in order to draw out conclusion from that data to solve real life problem. I like to use a simple analogy to actually explain the definition of statistics, and it is the concept of extracting raw material from a region, a natural resources from a region, and processing this raw material into a finished goods to actually consume or solve real life problem. So let's take crude oil for example. Crude oil is actually a natural resources, and the engineering process is to just set up a structure that is going to extract out this crude oil and then process it, refine it to have a finished goods known as petroleum jelly, petroleum, among all those stuffs, and then use this final product, which is petroleum, to consume or to fuel our car or to solve real life problem. This is how I see statistics. And the natural resources in this case of ours is actually data, which we are going to come back to in few minutes. So that being said, let's talk about the types or the branch of statistics. So basically we have two types of statistics. We have the inferential statistics and we have the descriptive statistics. So in no particular order, I'm going to start with the descriptive statistics. So descriptive statistics is actually that branch of statistics that only helps us to collect, analyze, organize, and present our data sets without making conclusion or solve real life problem with that data set. Using the same analogy of the production, the extraction process I said earlier, we can see descriptive statistics as that process that helps us to extract, that helps us to collect the natural resources, the crude oil, and convert it into a finished goods for us. But we are not going to be consuming that finished goods. We are not going to be using that finished goods to solve real life problems. So that is how I see descriptive statistics. Inferential statistics, on the other hand, is actually that branch of statistics that takes the details from descriptive statistics and use it to solve real life problem or make conclusions about the data. So using the same analogy, we can see inferential statistics as that branch of statistics, or as that branch of the process rather, that takes the finished goods, let's say petroleum in this case of ours, and use it to fuel our car or use it to solve real life problem. So that being said, it's time for us to talk about one of the most important details when it comes to mathematics, whether we are doing mathematics or we are doing applied mathematics or pure mathematics or statistics. This is actually quite important for us to talk about, and I'm talking about the concept of a variable. So let's define a variable. So in simple terms, a variable is actually that quantity whose value can change over a period of time. So it's actually that simple. And contrary to the concept of a variable, we have something we call a constant. So a constant is actually that quantity whose value does not change over a period of time. So it has a fixed value. So a variable has a changing value and a constant has a fixed value. In the general terms, we actually use lowercase to represent variables and we use uppercase to represent constant. I'm not saying you can't use any letter to represent constant or variable, but most times, most textbooks, they prefer to use lowercase to represent variables like X, Y, Z, A, B, C, D, and they prefer to use uppercase to represent constants, otherwise stated, depends on what you want to use to represent either your variable or your constant. So there are several types of variable in mathematics. In fact, we have a whole lot of them. There are quite much, but I'm going to touch the ones that we need for statistics only. So to mention a few, I'll be starting with what we call the independent variable. We have the dependent variable, we have the nominal variable, we have the ordinal variable, we have the discrete variable, we have the continuous variable, we have the numerical variable, we have the categorical variable, to mention a few. So to make things easier for us, I will just be defining just two variables right now. That is the independent and the dependent variable. And as time goes on over the course of this video, we are going to be defining the other types of variable that I just mentioned. So let's define independent and dependent variable. So as the name implies, independent, dependent, is actually quite easy for us to be able to define these variables from their names. It's that easy, but I like to explain the basic concept of independent and dependent variable from the basis of a simple law. So there are a lot of laws I can consider in mathematics, in physics, to actually explain the basis of independent variable and dependent variable, but I prefer to use the simple law of demand. So the law of demand states that the price of a commodity is actually dependent on the quantity demanded. That is, the higher the price, the lower the quantity demanded, and vice versa. So we have two variables right here. We have the price, which is one of the variable, and then we have quantity, which is also one of the variable. Now the law of demand states that the price of a commodity is actually dependent on the quantity demanded. So that simply implies that if you increase the price of a goods from, let me say, from $5 to $10, then the quantity demanded is definitely going to reduce. So that simply implies that price in this case of ours is actually the dependent variable, and the quantity demanded is the independent variable. So to define it, to give it a definition, so the independent variable is that variable in a function that its value does not depend on any other variables. In fact, it is being dependent on. So while the dependent variable is that variable in which its value is actually dependent of other variables. Preferably in mathematics and statistics, we like to use the letter X in lowercase to represent an independent variable and the letter Y in lowercase to represent the dependent variable. But like I said earlier, this can change. It's just based on perspective and it's subjective. You can decide to use letter A to represent your independent variable. Use any letter that suits you to represent your independent variable. So after defining the concept of variables and the independent and dependent variable, now it's time for us to move into this natural resources in which the whole of statistical process depends on. You see, the whole of statistics actually depends on data. If you can remember the analogy I used, I said we have an extraction process. We have a natural resources, and then we have a process that tries to extract out these natural resources rather, and actually use it to refine these natural resources and use it to solve real life problems. So the natural resources right here deposited in a region, in this case of ours, is actually data, and statistics is the process or the structure that we use to extract, to analyze, to present this data and refine it. So we need data in statistics. No data, no statistics. So that simply implies that data is really important in the concept, in the world of statistics rather. So let's define data. You see, anyone can define data any way they want to. It doesn't have there is no specific way of defining data in statistics. So I'm going to define data the easiest way I can, and I see data as a collection of useful information. In brackets, variables. A lot of variables make up a data. So let's say it again. A data is the collection of useful information regarding a group of things or a group of people. So to make things a bit easier for us, I will take an example. So let's assume I come to your university or I come to your school, and then I ask the school management to give me the age of individuals in the school. That is a data. That is an information about the students in the school. That is data. Or I can tell them to give me the height of students in that school, or I tell them to give me the amount of money the students pays per semester or per session or per term. So these are data sets. These are useful information regarding a group of people or a group of things. So before we move forward and talk more on data, we have to talk about the source of data. And most times in statistics, we get our data set from either a population or a sample. So that simply implies that we have to talk about the concept of population and sample. So let's go into it. Just like the definition of data, the population data does not have a definitive, I won't say definitive, it does not have a general definition. You can define a population data the way you want to define it, and you can define a sample data the way you want to define it, as far as you mention the key attributes of the population. So let me define population the way I feel it's easy for everyone to assimilate. So a population data is the total, emphasis on the word total, is the total available data regarding a group of people or a group of things. So one of the properties of a population data is that it is actually extremely large. It is usually large. Another property of a population data is the fact that if you decide to analyze a population data, it takes a whole lot of time to analyze it. It is also financially demanding to analyze a population data. That is, you need a whole lot of money to actually analyze a population data. Take for example, the country you are right now wants to conduct a population census. That is a whole lot of data, so it's going to take a lot of time. So that's why you see that whenever census wants to be done in some countries, it takes as far as 2 weeks, 3 weeks, where the country will be on shutdown. It takes a lot of money, it takes a lot of time and energy. So population data is usually large. It takes time to analyze it, it takes a lot of energy to analyze it, and it also takes a lot of money to analyze it. So examples of population data includes the total number of people in a country, the total number of cars in a university system, the total number of people living in a neighborhood, and so on and so forth. So let's define a sample data. So statisticians realize that they need the details present in a population to actually make statistical analysis, but population data has its downside. Yes, it has all the necessary details needed for statistical analysis, but yet it requires a lot of time to work on it. It requires a lot of money. So why not take an extract of the population and work on this extract, then use this extract to make an inference about the population? And this is where the concept of sample comes inside. So in simple terms, a sample is actually an extract, or we can say that a sample is a fraction of a population. So in the ideal world, in the simplest world, a sample is supposed to be the perfect representation, or we can say the exact representation of a population, but that is not true. We will get to know more about this when we get to the concept of sampling and estimation, I think in the next few videos, but let's just take it. In the ideal world, the sample is supposed to be the exact image of the population. So that being said, so a sample is actually an extract of a population. A sample is a fraction of a population, and it is easier to analyze a sample compared to a population. So if the total number of people in a country is let's say USA for example, so if the total number of people in USA is actually a population data, so the number of people in New York City, which is a state that is a fraction of USA, is a sample data. If the total number of students in the university is a population data, then the number of students in a specific faculty, let's say faculty of science or engineering, is actually a sample data rather, and so on. So now that we've defined the population data and the sample data, we are still going to come back to this when we get to estimation and sampling, but let's just get this definition of population and sample done with us. So that being said, let's try to talk about the types of data, because this is where it gets important and interesting. So in statistics, there are basically two types of data. We have what we call the qualitative data, also known as the categorical data, and we have the quantitative data, also known as the numerical data. So let us start with the qualitative or the categorical data. As the name implies, qualitative or categorical simply means a data set that can never take a numerical value. We cannot attach a number to it, and most times it is actually being used in grouping or in categorizing our data set. So examples of a categorical data or a qualitative data includes your gender, your state of origin, the type of operating system you have on your phone, either the iOS or the Android, the type of operating system you have on your laptop, either Windows or Apple, the type of color that you like, the type of food, and stuffs like that. So these are actually things we use in grouping people, we use in categorizing people without attaching a number to it. So since since categorical data rather are actually not numerical in nature, they don't have a number attached to them, there's a limit to the analysis that we can do with them, and that is just that the only thing we can do to them is to count them and most times or sometimes actually rank them. So we can only do two things with a categorical data. It's either we rank it or it's either we count them. So that being said, let's move to the second type of data, and that is the quantitative or the numerical data. And this is the type of data you are going to be most time working with in the world of statistics. I'm not saying you will not meet the qualitative data in real life. You will, but most times in statistics you come across quantitative or numerical data. So a quantitative or a numerical data is that data set that can take a numerical value that we can attach a number to it. That is, it is quantifiable. So examples of quantitative or numerical data includes time, it includes speed, includes acceleration, includes pressure, includes amount of money, includes stock prices, includes supply, and details like that. So that being said, we also have the types of quantitative data, and there are basically two types of quantitative data. So we have what we call the discrete and the continuous data, and this is where it gets more interesting. So the first question is, what is a discrete data? So if you try to check this with the dictionary, like you want to check the meaning of discrete, it simply means something that is finite, something that is countable. So in simple terms, it simply implies that a discrete data is that type of data set that is finite, that can only take finite number of values, and that is also that can only take countable number of values. So that being said, let us try to get some examples of discrete data. For example, the number of students in a class is actually a discrete data. The number of cars parked in a garage is also a discrete data. These are countable values. For example, I can tell you that in this class we have 10 students. That is a countable number. That is an whole number. In this garage we have 50 cars. That is a countable number. You can't tell me that in this class I have a number of 4.5 students. That is wrong, because a discrete data can't take a decimal value. It's not possible for the number of children in a class to be decimal, to be 4.5, to be 4.3, to be 4.2. So once again, a discrete data is said to have only countable number of values, and it can never take decimal value. So let's run through the summary of discrete data. Number one, it is countable. It must be countable. It can take only finite number of values rather, and it does not take decimal values. On the other hand, we have the continuous data set, and for a continuous data set rather, it is that type of data set that can take infinite number of values. So there's a range of values. There's a range rather in which the values of continuous data set can come from. And secondly, it is a continuous data is not countable. It is actually measured. So and thirdly, a continuous data can actually take decimal values. So examples of continuous data include height, include age, includes amounts of money spent, includes price. So that begs the question, is age a continuous data or age is a discrete data? And here is what I'm going to say. Age is actually a continuous data, because it is possible for somebody to be 20 years old and 6 months, and 20 years old and 6 months translates to 20.5 years, and that is a decimal value. So it's also possible for us to have 20 years, 6 months, 10 weeks, 5 days, 2 minutes, and stuff like that. So we can keep having the age to several decimal places. So age is actually a continuous data and not a discrete data. Oh, and if you're enjoying this video, by the way, a sub to the channel will be continuous. Alright. Yes, I remember saying that I'm going to touch the other types of variables we have in statistics, and that being said, so I've mentioned a categorical data set, and the variables that make up a categorical data set rather are known as categorical variables, and the variables that make up a numerical data set are known as a numerical variable. The variables that make up a discrete data set is known as a discrete variable, and the variables that make up a continuous data set is known as a continuous variable. So that being said, it's time for us to talk about the levels or the scales of measurements of data. So basically, there are actually 4 levels, or we have 4 scales that we use to measure data, and we have what we call the nominal scale, we have the ordinal scale, we have the interval scale, and we have the ratio scale. So let's take it one after the other, and we start with the nominal scale. So for a nominal scale, we have a scale that is actually qualitative, that is a scale that cannot take a numerical value. And for a nominal scale, the only thing we use to work with a nominal scale is we use it to label our data, or we use it to group our data. So examples of nominal scale includes gender, includes the type of food you like, the type of color, your country of origin, your state of origin. So once again, a nominal scale is actually qualitative. It cannot take a numerical value, and it is basically used in labeling or in grouping. The second type of levels of measurements that we have is actually the ordinal scale, and the ordinal scale is actually a nominal scale that has ranking attached to it. So we can say that an ordinal scale is this scale of measurements that is used in labeling or grouping, and it's also used in ranking our data set. So examples of ordinal scale is going to include the socioeconomic status, that is either you're in the middle level, the low level, the high level, or the middle level, meaning the low class, the high class, or the middle class. What did I just say? Okay, this is low class, high class, and then the middle class. So we also have the military rank. So in the military rank, we have those in the the 5-star, we have the 4-star, we have the 3-star, we have the 2-star, and we have those details. We also have the satisfaction level when you actually consume a goods or service. So you can actually be extremely satisfied, or you can actually be angry, or you can just be in the middle. Whenever we are also playing games, to the difficulty levels is actually also an ordinal scale, meaning it can either be the professional, the beginner, the amateur, like the hardest, the easiest, the medium, and details like that. So one thing we've noticed is that both the nominal scale and the ordinal scale are actually qualitative in nature. That is, they can't take a numerical value. We can't assign a numerical value. To them rather. So we have the interval scale and the ratio scale, and to explain the concept of the interval scale and the ratio scale, we have to pay attention to a little detail. And in fact, I have to use the concept of a meter rule or a ruler. So if you take a closer look at your ruler, you can see that your ruler has gradings. We start from 0, we have 1, we have 2, we have 3, we have 4, down to like 30 centimeter or 15 centimeter. The distance between each point on a ruler is actually the same thing. It's actually the same value. That is, between 0 to 1 is 1. Between 1 to 2 is actually 1. Between 2 to 3 is actually 1. Between 3 to 4 is 1, like that. So two successive values on a ruler or a meter rule actually have the same distance between them, and that is one of the properties that defines an interval scale and a ratio scale. So it's time to talk about the interval scale and the ratio scale, and I would like to start with the ratio scale. So one of the properties that is common or that distinguish the ratio scale and the interval scale is the concept of a true zero. And that brings the question, what is a true zero? So a true zero is actually that point on a scale that tells us that it is possible for us to have a zero value of the variable of interest. So let me try to make this easier for us. It is possible for someone to have 0 years of experience when it comes to a job. It is possible for someone to have 0 number of children. It is possible for someone to have 0 amount of money. So that is just the basic definition of a true zero, a point on a scale whereby the variable of interest has a 0 value. Now, one of the distinct property of a ratio scale is that a ratio scale actually has a true zero, meaning it has a defined center point. And since it is a ratio scale, it means that 2 points on the scale can actually be divided by each other. So we can say that the amount of money Mr. X owns is 2 times the amount of money that Mr. Y owns. That simply makes sense. So let's say another example is that we have like someone X and someone Y, and we can say that the age of X is actually twice the age of Y. So that means that X over Y is actually equals to 2, or we can say X is equals to 2Y. So that means the age of X is actually twice of that of Y. So that simply implies that we can actually divide the values on the ratio scale, and they also have a true zero. So this is the property that defines a ratio scale. So let's go to the interval scale first and define, and then we'll move back to the ratio scale. So an interval scale, on the other hand, is everything we can think of. An interval scale can be used to label, it can be used to group, it can be used to rank, and it can also take a numerical value attached to it. So I see an interval scale as an ordinal scale with a numerical value attached to it. And then one of the properties of an interval scale is that it does not have a true zero, meaning it does not have a definitive center. So most times an interval scale can take a negative value. So since an interval scale does not have a true zero, it simply implies that we cannot divide two values on the scale. For example, examples of interval scale includes the SAT scores, we have the pH scales, we have the centigrade scales, and we have the Fahrenheit scale. So if someone scores 300 in SAT and the other person scores 600 in SAT, the person that scores 600 does not mean he did 2 times the job or is 2 times better than the person that scored 300. It doesn't work that way. So that being said, a ratio scale is the next we're supposed to talk about. And like I said earlier, so a ratio scale is the most complete type of scale in statistics. I repeat, the ratio scale is the most complete type of scale in statistics because it can be used to group, it can be used to rank, it can be used to label, it can take a numerical value, and it has a true zero. And since a ratio scale has a true zero, it simply implies that values on this scale can actually be divided. That is, we can have a ratio. So that simply implies that we can say that this person, like I said earlier, this person is X age and this person is Y age, and the age of person X is 2 times the age of person Y. That is, X is equals to 2Y, and we can also say that X over Y is equals to 2. Also, the number of years of experience is also something on a ratio scale. So we can say that if this person's number of experience of years of experience is X and that is Y, so X can be equals to 3 times of Y. So examples of ratio scales includes age, we have pressure, we have the Kelvin temperature scale. And that is all we have for today. In our next video, we talk about the numerical and the visual analysis. And if you enjoyed this video, a sub to the channel will actually be really appreciated.